Welcome to The Explainer. I am absolutely thrilled to have you here today. If you're the kind of focused learner who loves to decode the logic of the world around us, well, you are exactly in the right place. Today, we're taking what seems like a super basic elementary math rule and we're going to transform it into a really profound look at how the entire universe is organized. We are tackling the commutative property. We all remember learning it in school, right? But the implications of this rule when it works, and more importantly, when it completely falls apart, are genuinely fascinating. So let's dive right in. To kick things off, I want to hook you immediately with this core question. Is the commutative property limited to numbers only, or can it be used anywhere in this world? It's such a brilliant premise. We're going to test if this mathematical principle is just a convenient little trick for balancing your checkbook, or if it's actually a fundamental law governing physical reality. Just keep that question in the back of your mind as we go. Section 1, the rule of order. Okay, before we can start breaking the rules of the universe, we kind of need to establish the absolute foundation of what this mathematical property actually is and what it claims to do. Simply put, the commutative law is a rule defining a change in order. That's the whole core concept right there. The focus is strictly on changing the positions of the operands, and the operands are just the things we're interacting with, right? The numbers, the variables. This law is entirely about what happens when those elements just swap places. Does reality stay the same, or does it change? What's really comforting and familiar about this pattern is the perfect visual symmetry. Think about basic addition. 2 plus 3 equals 5. Swap the order. 3 plus 2 still equals 5. What about -9 plus -7? That gives you the exact same result as -7 plus -9. When we change the numbers' positions in addition, the end result remains entirely unchanged. It is safe, it's predictable, and it's perfectly balanced. And this totally holds true for multiplication, too. Whether it's 2 times 4 or 4 times 2, you are getting 8. Even with larger numbers, 13 times 15 equals 195, and 15 times 13 is still 195. Even throwing negative numbers into the mix doesn't shake the foundation. The pattern is crystal clear here. Changing the order or the position of the numbers in multiplication does not affect the result. So far, the universe seems perfectly reversible. Chapter 2. Breaking the pattern. But of course, it's never quite that simple, is it? This is the twist in our narrative. This is the precise moment where that neat, beautifully symmetrical rule we just established suddenly ruptures. When we contrast the safe, unchanged results of addition against the totally different reality of subtraction, things get wild. Where addition leaves things unchanged, subtraction creates a complete 180-degree opposite output. The symmetry doesn't just bend here, it completely shatters. Just look at how this plays out in subtraction and division. 3 minus 2 equals a positive 1. But flip that order, 2 minus 3, and you drop below 0 to a -1. Positive 1 is absolutely not equal to -1. And that exact same completely order-dependent chaos happens in division. 10 divided by 5 is 2. But 5 divided by 10? That's 0.5. The operation itself dictates everything, and the commutative property just totally vanishes. So the crucial point here is understanding the underlying logic. In the commutative law, the impact is isolated entirely to the result. The operands, the 3, the 2, the 10, the 5, they remained completely unchanged as constants or variables. We are literally just playing with their seating arrangement. But as we just saw, depending on the rules of the operation, that simple change in seating can shift the final reality dramatically. Section 3, Real-World Geometry. All right, it's time to zoom out from abstract numbers on a chalkboard and answer that main question we posed at the very beginning of this explainer. Why do we actually need to study this? How does it apply outside the classroom? Well, I absolutely love this relatable example because it really grounds the abstract math. Imagine a physical flower bed in your yard. If it's 4 meters long and 3 meters wide, the physical space you have to plant in is 12 square meters. Now, if you rotate that exact same flower bed so it's now 3 meters long and 4 meters wide, your area doesn't magically shrink or grow. It is still exactly 12 square meters. Length times width equals width times length. Physical space literally demands commutativity to make sense. And the coolest part? Humanity has intuitively understood this for millennia. This mathematical concept connects to some incredible human history. There are these ancient Indian texts called the Solba Sutras, and they were actually used by craftsmen for designing highly specific fire altars. Long before modern algebra classes, these ancient craftsmen utilized these exact geometric symmetries. They deeply recognized that the physical space occupied remained constant, no matter how you rotated the length and the width. Chapter 4. The 19th Century Name. Now, even though this concept is incredibly ancient and totally fundamental to human construction, giving it a formal, official name is a surprisingly recent development. Just look at the timeline. In ancient times, like we just saw with the Solba Sutras, the concept was practically applied in architecture. Then, for centuries upon centuries, mathematicians just kind of took the property for granted. It was so completely obvious that 2 times 3 is 3 times 2 that literally no one bothered to officially label it. It wasn't until the year 1814 that it finally got a name. And here is the man behind it. The term commutative was coined by the French mathematician François Servoy. He derived it from the French word commuter, which means to switch or substitute. But why did he bother naming it in 1814? Well, because as mathematics grew increasingly complex, experts realized a startling, unavoidable truth. Not everything commutes. Once math evolved past simple addition and multiplication, they desperately needed a specific name for this behavior because it suddenly became the exception rather than the rule. Section 5. Beyond basic numbers. So we are now going to push completely past elementary mathematics and look at what happens when we apply these concepts to the highly complex laws of the universe. Let's break down the profound limitations of the commutative property. When we enter higher-level fields, we encounter strict order dependency. The commutative property fails in matrices. It fails in advanced mathematical functions. It absolutely fails in physics, and it fails in direction-based scenarios. Basically, in these advanced fields, the order of operations fundamentally dictates reality. Real-world physics and higher mathematics are incredibly order-dependent. Think about a direction-based scenario, like navigation. If your instructions are walk forward 10 paces, then turn right, you end up in a very specific spot, right? But if you commute the order, turn right, then walk forward 10 paces, you are heading in a completely different direction to a completely different destination. The first direction you choose fundamentally alters your final outcome. The commutative law is absolutely useless there. So I want to leave you with this mind-expanding thought. If higher mathematics, complex physics, and basically most real-world actions in life itself are strictly order-dependent, is the commutative property, that safe, reversible little math rule we all learn in grade school, actually just a rare, lucky exception in a deeply ordered, irreversible universe? Definitely think about the true nature of order and symmetry the next time you're just doing some basic math. Thanks so much for joining me on this explainer, and keep questioning the world around you.